Yavaş yavaş başlayabiliriz arkadaşlar. Okay. So first of all, do you have any questions? Okay, you can write in the chat if you want, if you have a question. So let's review what we did yesterday. Quickly review what we did yesterday. So we started something new, right? We started this vector space, and vector space. So the idea really comes from the usual vectors in the plane and in tree space. Okay, so yesterday we quickly reviewed some of these properties. So the vectors in the plane, like these, or vectors in the tree space like these, they have certain relations. Okay, so there's a vector addition operation and a multiplication with scalars, and they satisfy certain properties. Okay, and we look at those properties and then said, okay, so it turns out that R2 and R3 is not the only structure which has these properties. There are other objects. Okay, so and we call this general notion a real vector space. Okay, so a real vector space is a set, and it has two operations. One of them we called O plus and one of them we called O dot. So if all these properties are satisfied, so we have here we have in fact 10 properties. Okay, so we have property A and property B, and then we have 4 properties here and 4 properties here. Okay, so the first group is the properties about vector addition, and the second group is about the operations on scalar product. Okay, so okay, we did these things. Then we look some of the examples. Okay, the first structure is, of course, the usual vectors in the plane and in tree space automatically satisfy all these properties because we were inspired by the properties in these structures, right, to define this vector space. So they satisfy that. Not only R2 and R3, but in general, like any, like the set of vectors, the set of all vectors in Rn satisfy those relations, properties. Okay. And after that, we talked about matrices. Matrices are also form vector space. We first started with 2 by 2 matrices, and then we generalize it to m by n matrices. Okay, m by n matrices are also vector space. Now, vector addition in this case is matrix addition, and scalar product is scalar product with matrices. So matrices form vector spaces. Okay, this was an example we skipped yesterday. I think I will talk about it today. Then we look at some non-standard examples such as polynomials. Okay, so P2 is the set of all polynomials with degree less than or equal to 2. And this is a vector space. Okay, now we consider each polynomial as a vector. Okay, each polynomial is a vector now. What is vector addition? Vector addition is now polynomial addition. What is scalar product? Scalar product is the product of polynomials by numbers. So this set P2, this structure P2 is an example of a vector space. Okay, and not just P2, but Pn, the set of all polynomials with degree less than or equal to n is a vector space. We can even generalize this, the set of all polynomials with not just fixed degree, but all polynomials with any degree is a vector space. And in general, the set of all functions is a vector space. Okay, so much of the modern mathematics depends on this notion of vector space. Okay, so in higher mathematics, a lot of the structures you see there are vector spaces. Let's go. So these are the things we did yesterday. Then we look at some non-examples. For example, so V is the set of real numbers, and we define this vector addition as multiplication. I'm sorry, subtraction, okay? Then this is not a vector space because it does not satisfy those listed properties. For example, it does not satisfy this property, right? 3 plus 2 is not the same as 2O plus 3. Okay, so what is this? This is 2 minus 3, which is minus 1. Okay, you see the issue here. So if you define the vector addition as subtraction, then it just doesn't work. Okay, so you cannot change the order of the terms. So we did some other examples, so I'm skipping those things. Okay, we looked at some properties, and then we were talking about these subspaces. This is where we stopped yesterday. I mean, we did some of these things as well. So what is a subspace? So we have so a vector space V, right? And we have a subset of it. So we show it with this symbol. So W is a subset of V, and V is a vector space, okay? So V is a vector space. And if W is a vector space as well, if W is a vector space, then we call W a subspace of V, okay? Okay, now to check that W is a vector space, you have to go back to the definition and you have to check all those properties, right? All those like 10 properties that we have listed. Well, it turns out there's an easier way. What is the easier way? So it turns out that if W is a subset, if W is a subset of a vector space V, then you only need to check two properties. Okay, if these hold, the other will automatically hold. So out of those 10 properties, only property A and property B must be checked. What was property B? Property B is closure under vector addition, okay? Closure under vector addition, meaning that if U and V is in W, then you require U vector addition V is in W. This is property A. And property B is if U is in W and C is any scalar, then you require CO dot U to be in W. So if these properties are satisfied for all possible U and V and all possible C, then the result, so then this W turns out to be, this is not a good color. So then this W becomes a subspace. Okay, so checking that a given checking that a given subset is a subspace is much easier to prove than showing that it's a vector space. Okay, so instead of those 10 items, you just look at 2 of them. That's good. So there are 2 subspaces which are called trivial subspaces, and regardless of which vector space you are working, so regardless of what V is, this vector space 0 is always a subspace. So this is a one element subspace. It's not very useful, but it's good to know that such a subspace exists, always a subspace. And there's another subspace of V, which is V itself. This is also always a subspace, right? So any vector space is a subspace of itself. So this is kind of trivial. Any questions? Okay, no. Then, for example, we looked at this example, P2. What was P2? P2 is polynomials of degree less than or equal to 2. And this is a subset of all polynomials, okay? So if we show this is a vector space, the set of all polynomials, then to show that P2 is a vector space is easy. All you have to do is check that sum of two polynomials whose degree is less than or equal to 2 is also a polynomial whose degree is less than or equal to 2. This is the first thing you need to show. And the second thing is any polynomial of less than or equal to 2, if you multiply it with a scalar, the result is a polynomial whose degree is less than or equal to 2. And both of these are trivial, kind of trivial. Because if you add two polynomials of degree of in this form, then the result is, you see, it's again, so there should be an x here. I think I forgot to write it. So the result will be a polynomial of at most degree 2. It can be less than degree 2, but it cannot be greater than degree 2, okay? Because if this number, c plus f, is 0, then the polynomial will become degree 1 or degree 0. Any questions? Okay, for example, if you look at this example, is the set of all polynomials of degree exactly to a vector space? The answer is no, because if I add this one, which is a polynomial of degree 2, to this one, which is also a polynomial of degree 2, then the result is x plus 1, which is a polynomial of degree 1, okay? So this given set is not a vector space, okay? Okay, so what is the next thing? Okay, this was the last slide we were talking about. So we did this one, right? So we looked at the plane, the vectors in the plane, right? Vectors in the plane. So we want to find certain, we want to show whether given subset is a subspace. For example, the first thing we looked at was vectors of this form, x, y, where the first component is a non-negative number. Is this a subspace? So we can geometrically show it like this. So in the xy plane, the first coordinate being greater than or equal to 0 means the right-hand side with y-axis included, okay? So this is I hope I'm recording, by the way. Let me check it. Yes, I'm recording. So this place, this region is not a subspace. If you remember, because if we take, let me show it with a different color. If we take a vector like this, and if I multiply this by -1, I get a vector in the opposite direction, which is not in that region. Okay, so this given subset is not closed under scalar product. Any questions about this? So if I take this vector, if I multiply it with -1 or -2, doesn't matter, you end up in the opposite direction, which is not included in this set. Okay, so this is not a subspace. Okay, and then we look at this example, right? The set of all vectors whose first component is 0 and the second component is any number. Well, it turns out that this is a subspace, because if you add such vectors whose first component is 0, then the result will have the first component 0. So it will be in the same set. And if you multiply these vectors with scalars, with numbers, then the result is still in of this form, because C times 0 is 0. Okay, so this one is a subspace. So in part B, this is a subspace, and part A, not a subspace. Then I said something about so subspaces of R2. Subspaces of R2 are exactly lines passing from the origin. So R2 itself, the whole plane itself is a subspace, and any line passing from the origin is a subspace. And finally, the zero vector. Zero vector means the origin is a subspace. There are no other subspaces of R2. Okay, so this is X, this is Y. So subspaces of R2 are lines passing from the origin, which can be also this line, right? The whole plane and the zero vector. Okay, we have seen that the zero vector and the whole of the vector space is always a vector space. Any questions? So this is what we did yesterday. So I tried to go over it once again. Let me know if you have any questions. So now let's look at this example. Is the set of all vectors of the form A, B, A plus B a subspace of R3? Try to think about this for a minute, okay? And let me know. Let me know what you think about it. Okay. Do you think the answer is yes or no? Yes. So some people are claiming the answer is to be yes. So let's check it. So how do we check it? So we have to check two properties, right? The property A says, take two such vectors, A, B, A plus B, and take another one and add them. Let's say C, D, C plus D. So if you add them, is the result of the same form, A plus C, B plus D, and A plus. So what is the result here? So if I add these things, I get A plus C plus B plus D. So I wrote it in this form. So let's go back. So to be in this set, the requirement is the third coordinate is the sum of the first two coordinates, okay, A and B. So the third coordinate must be a sum of the first coordinate. Let me give an example. For example, 1, 2, 3 is in the set. But what I don't know, 4, 5, and 0 is not in the set. Okay, this is just an example. So if I add them, I get this result. So is this result still in the same set? So is the third coordinate sum of the first two coordinates? Yes, right? Yes. So So the first condition is satisfied. Let's check the second condition. What does the second condition say? Second condition says, take any number k and multiply it with a vector of this form and see if the result is still in this form. So what do I get? Ka, kb, and ka plus kb. So is the result still in this form? So is the third coordinate sum of the first two coordinates? Yes. So you see that this is correct. So this is also hold. So the both properties hold. So yes, the answer is this is a subspace. So remember, the only thing we have to check is these two conditions. Okay. Okay. Any questions? Okay, let's look at this next example. So if we are given two vectors, v1 and v2, in a vector space, okay, we don't know what this vector space is. It can be anything. It can be the vector space of matrices. It can be the vector space of polynomials. Nothing is mentioned here. So any vector space. And we take two vectors in, v1 and v2, okay? It says, show that the set of all vectors, which can be written like this, is a subspace. So what is this set? This set is the set of all vectors which can be written in this form. For example, 3v1 plus 5v2. So let's give a name to this set, W. Let's call it W, okay? So 3v1 plus 5v2 is in W. And in general, for any A1 and A2, okay, for any real numbers, A1, A2 is in this set. So the question is this set a subspace? Okay, we have to check two properties. Let's look at these properties. So we take two vectors in this set. So we know that the vectors in this set can be written in this form. And we add them, okay? This is the first vector. And the second vector is b1, v1 plus b2, v2. Here, b1, b2, and a1, a2 are numbers, okay? So if we add them, you see the result is still of the same form. Why it is still of the same form? Because to be in this set requires the vectors in this set are of this form. A const, like a number times v1 plus a number times v2. Okay, so whatever these numbers are, this is in W. Okay, so this is an element of W. So the first condition is satisfied. And let's look at the second condition. If I multiply a vector in this set with a scalar like k, then what is the result? The result is ka1 v1 plus ka2 v2. So this is still of the same form. So this is an element of W because it's a some number times v1 plus some number times v2. Okay. So these, if these two properties are satisfied, then we say yes, this is a subspace. Okay. So we will see that this example is kind of important because most of the examples we will see will be in this form. Okay. So this is an important example. Since this is an important example, let's give a definition related to this example. Now, again, we take some vector space, okay? We don't specify which one is it. It's an arbitrary vector space, and we take k vectors in it. Then, if if I write something like this, where a1, a2, ak are numbers, and v1, v2, vk are these chosen vectors, I call this whole thing, which is a vector, a linear combination of these vectors, v1 to vk. Okay, let's give some examples. Let's give some examples. For example, let me take v to be r2. So I am talking about vectors in the plane. Okay, so I take 1, 2 to be v1, and I take v2 to be 3 and 5. Now, for example, 2v1 plus 3v2, what is this? Let's compute. This is 2 plus 9 and 4 plus 15. What is this? This is 11 and 16. So the vector 11, 16 is a linear combination of these two vectors, v1 and v2. Okay, so according to this definition, since I can write 11, 16 as a multiple of v1 plus a multiple of v2, it means 11, 16 is a linear combination of, this should be v2, 11 linear combination of the vectors 1, 2, and 3, 5. Yanlış mı yapmışım? Evet, 19 olacakmış. Okay. Is this okay? Let's give different examples. What is it here? Let me give another example. Let's give another example. What should we give? The question is, so this time let's take V to be P2. So remember what P2 is? So this is vector space of polynomials degree less than or equal to 2. Okay, so the question should let's write a question. So let's take P1 to be I don't know, 1 plus x squared, and P2 to be I don't know, 3 minus x. No, let's write 1 minus x. Okay, so we take two vectors in this vector space. Now the question is this. Question is I don't know, 1 plus 2x plus x squared a linear combination of P1 and P2? This is my question. What do you think about this? Let's pause for a minute and what do you think? So let me make this bigger so that you'd see the definition. What do you think about it? Carl Johnson. Yes, I think. Artık sizleri tanıyamıyorum arkadaşlar. Yes. Some people think it's yes. Let's look at it, okay? Some people think it's no. That's good. Not everybody agrees, okay? So let's see. So what is our definition saying? So our definition is this. So the question is really this. Can we write this polynomial 1 plus 2x plus x squared as a linear combination? Means a1 times the first guy, 1 plus x squared, plus a2 times the second guy, which is 1 minus x. So can we find such numbers? So we reduce the question into this one. Okay, so let's look at it. So what does this mean? So this means 1 plus 2x plus x squared is, let's first look at the constant terms, which is a1 plus a2, right? This is the constant term. So if I add, I get, what is it? Minus a2 times x. And what are the x squared terms? a1 times x squared. Okay, so what do we see? So let's choose green color. So let's look at these terms. So you see that for this to hold, a1 must be 1. And then we look at x terms, which means a2 must be minus 2. So finally, what is, let's look at these parts. a1 plus a2 must be 1. So can such a1 and a2 exist? You see there's a contradiction here, right? Because if a1 is 1, a2 is minus 2, then their sum is minus 1, not 1. So the answer is no. No such a1 and a2 exists. No such a1, a2 exists. Okay, guys, can you follow this? Do you have questions? Evet arkadaşlar, mikrofonunuzu açıp da soru sorabilirsiniz isterseniz. İlla chat'e yazmanız gerekmiyor. No. Okay. Shall we do one more? Yeah, let's look at one more example. Okay, this time I will give an example regarding the vector space of matrices. Okay, 2 by 2 matrices. So this is a vector space. We discussed this in the last lecture. So my question is this. So let's come up with some matrices. Is I don't know. So let's try to think about it. 1, 1, 2, 0, a linear combination of the first matrix V1 is 1, 1, 0, 0, and the second matrix is 1, 1, 1, 0, 0. So this looks kind of, how does it look? And let's write the third one. And third one is, I don't know, 0, 1, 1, 0. I don't know the answer. I think the answer will be yes. So is this given matrix a linear combination of these three matrices? Let's look at it. So what is at stake here? So we need to show whether this given matrix can be written as A1 times V1, which is 1, 1, 0, 0, plus A2 times V2, which is 1, 1, 0, 0, plus A3 times V3, 0, 1, 1, 0. V1 plus V3. Is it V1 plus V3? Wow, you're right. So you're right, Kramer. Shall I call you Kramer? I don't know. Okay, so let's look at the this result here. So what do we have here? So if I write these things, I get A1 plus A2. What is the second component? A2 plus A3. And what is this one? A1 plus A3. And this one is 0, okay? So we get this. So from this equality, we have three relations. A1 plus A2 is 1. A2 plus A3 is also 1. And A1 plus A3 is 2. So can you solve this three equations for ABC, A1, A2, A3? So does this system have a solution or not? Well, this really looks like, so in general, this really looks like the systems we have seen in the beginning of the class. Okay, so we're trying to solve this system for A1, A2, A3. So you can do it. For this system, it's easy, but in general, how do you solve it? Well, to solve it, you form this augmented matrix. Like this. So what is the solution for this one? Yes, Carl Johnson, you have seen the solution, but I'm trying to do something which can be applied to like any general problem, okay? So what we do is we reduce this matrix, right? So we multiply the first row by -1 and add it to the third row and replace it with the third row, like this. So what do we get? We get 1, 1, 0, then 0, 1, 1, and then I get 0, -1, and 1, and this is 1, 1, and 1. Then what do we do? So we need to get rid of, so at first we want to get rid of this, now we want to get rid of this. Okay, so what do I do? No, not this one. So I like this green color. Okay, so this is R2 plus R3 to R3. If you do that, what do we get? We get 1, 0, 0, and then 1, 1, 0, and then 0, 1, 2, and 1, 1, 2. Okay, now this is almost in reduced form. So from this, we can solve for A1, A2, A3. So this means 2A3 equals 2, which means A3 equals 1. And then we get A2 plus A3. The second equation is 1. So since we know A3 is 1, A2 must be 0. And let's look at the final equation, A1 plus A2. equals what? 1. A2 is 0, so A1 must be 0. So the important thing is not these numbers, but the important thing is this system has a solution, okay? So yes, this system has a solution. The answer is yes. A1 1 hocam, doğru. Ben niye 0 yazdım? Okay, so this is 1. Okay. Any questions? Okay, we have 2 more examples. I'm not sure if we can finish both of them. Okay, what does this say? Let's go over it. Okay, I think we looked at this example, the set of all vectors of this form. So the third coordinate is a sum of the first 2 coordinates. So this was a subspace of R3, okay? Subspace of R3. Let me write R3 like this. Okay, so the question is now this. Let's call V1 to be this vector and V2 to be this vector. Then what we can see is every vector in W is a linear combination of these 2 vectors. Why? Because any vector, so any vector is of this form, and I can obtain this form as multiplying the V1 vector by A and V2 vector by B and then adding it. Let's see. So if I multiply V1 by, so what is A times V1? Let's look at this part. So what is A times V1? So this is A, 0, A. Plus, what is B times V2? So this is 0, B, B. Okay, and the result is A, B, A plus B. So you see any vector of this form can be written as a linear combination of V1 and V2. What is the importance of this? We will see it, okay? So in a sense, we're describing like infinitely many elements like this by just 2 vectors, okay? This is very important idea that we will see in the next sections, okay? There are many elements, infinitely many elements here, and only 2 of them are necessary to describe all of them. Okay, this is a very important idea that we will see again in the future. Any questions about this? No? Okay, let's look at one last example. So let me close this remark. So we are again given a vector in this case, this is in 3 space, okay? So 3-dimensional vector. So the question asks whether it's a linear combination of these 3 vectors, V1, V2, and V3. Okay, we have 5 minutes. I think we can finish it. So let's try, can I do like this? No. Okay, I try something and it doesn't work. So how can I do this? Let me write here. So, oops. Let me write here. Oops. So I'm trying to write the vector 2, 1, 5 as a linear combination. So which means A times the first vector, 1, 2, 1, plus B times the second vector, 1, 0, 2, plus C times the third vector, 1, 1, 0. So the question is whether such ABC exists. Okay, let's look at it. Let's look at it. Let me write here. So what does this mean? This means so A plus B plus C equals 2, and then 2A plus C equals 1, and A plus 2B equals 5. So we're again in the same situation, right? So same thing. Can we solve this? Well, we look at the augmented matrix 1, 1, 1, 2, 0, 1, and 1, 2, 0, and then write these numbers 2, 1, 5. And then we have to solve this. We have to find whether this system has a solution or not. Okay. Let's try to solve this. So we start with trying to make these 0. Okay. So how do we do that? So we write minus 2 row 2 plus row 1 to row 2. I did it wrong. So this should be row 1 and this should be row 2. This should be row 1 and this should be row 2. And also minus row 1 plus row 3 to row 3. So what happens if you do this? Let's look at it. So we get the first line doesn't change. The second line becomes 0, minus 2, and then minus 1, and then this becomes minus 3, right? And the last line becomes 0, this becomes 1, and then this becomes minus 1, and then this becomes 3. Correct me if I make any mistakes here. Now, so I need to make this one 0, this entry 0, but there's another way here. So if I swap these two rows, I get a 1 here. Okay, so that's what I want. So here I'm swapping row 2 and row 3. And if I do that, I get 1, 0, 0, 1, 1, minus 2, and 1, minus 1, minus 1, and 2, 3, minus 3. Okay, so the last step is trying to make this guy equal to 0. How can I do it? Well, I can write 2 times row 2 plus row 3 to row 3. If I do it, I get 1, 0, 0, 1, 1, 0, and then 1, minus 1. What is this thing now? I multiply by 2, I get minus 3. What is this? 2, 3, and 6, and 3, right? I hope this is correct. So if I make any mistakes, so I think I have the answer here. We can check. Okay, so from the last line, we see minus 3 times C equals 3. So C must be minus 1. And then I have B minus C equals 3. So B is 2, right? B is 2. Then A plus B plus C is 2. And this gives me what? 1, A is 1, right? So the important thing, as I said, is not the actual numbers, but whether this system is consistent or not. Okay, so this system is consistent. It has a solution. So the answer is yes. So let's go back, check the answer. So again, okay, we are doing the same thing. I'm writing 2, 1, 5 as a combination of these 3 vectors. And I'm trying to solve for A1, A2, A3. Above, I called them as A, B, C, doesn't matter. So I look at this answer, this equations, and I try to solve it. Okay, guys, I think we're almost finished with this section. There's one more thing, so I will do it next week. And you can look at For your own study, you can of course check these videos on the UZEM website. You have the lecture notes, and you also have textbook. Okay, I'm giving you some exercises from the textbook. Please try to solve them. So this linear algebra is very important for you. You will see that in your engineering life, you will see lots of examples of ideas from linear algebra. So try to understand this material. If you have any questions, you can ask me. If not, you can leave the meeting now. Herkese görüşmek üzere arkadaşlar. Görüşürüz arkadaşlar. Kendinize iyi bakın siz de.